Okay, so good morning and happy Monday. Hope you all had a great weekend. Today, we're going to probably only get through half of the stuff in the slide deck. The balance of this I will cover on Friday. On Wednesday, we're going to have our written exam number two. And then after this week, we're going to cover or spend the rest of the semester on machine learning methods, the so-called extraction of insights. That'll have associated with it a project assignment. And the purpose of that will get you practiced is to get you practiced with using some of these APIs from scikit-learn, these machine learning APIs. And then our final project will involve all of the stuff that we've been using, and that will be a comprehensive project. And you'll be given 2 weeks from till the last day of finals in which to complete that final project. And the final project is the final exam for this course. Students seem to enjoy it from last semester, and some of them actually use the material in job situations as well. So, all right. So before we begin, the usual excuse me, administrative bits. Course written exam number two, I think Wednesday is the 12th, if I calculated it right. And after today, we have 3 weeks left of class. All right. I did look up the final exam schedule. The usual registrar from the usual email, I should say, from the registrar hasn't come in. I did look on the registrar's website at the general list for final exams. And it doesn't have an entry for this class. They do it based on the day of the week. And so when I get that information, I'll certainly send an email to the registrar after this class when I get back to my office. But when I find out specifically when our final period is, I will certainly let all of you know through a number of modalities. And so I'm banking on 8 o'clock in the morning. I seem to have the luck of the draw, so to speak, and my class is getting 8 o'clock in the morning. I'm hoping not, but my tradition is to spring for coffee and morning snacks. I don't know how I'm going to trudge that stuff across campus from my office. Question, yeah. Oh, we are on the general one. Do they do it by the class meeting or is it all three classes? I'm sorry. Yes. Okay. Because our class technically is Monday, Wednesday, and not Monday, Friday. I just use the Wednesday one as a lab section so that you'll have, theoretical module, practical, theoretical module. But I'll take another look at it. Thank you. Friday at 10:30. Okay. Okay. Oh, all right. Hmm. I'm not a fan of this room. That's the course grid. Is that the registrar's page? Okay, well, thank you. I looked at it and I couldn't find an entry for this class. I'll look again. Thank you. Any questions? No? All right. So today we're going to talk about the methods of doing parameter estimation, max likelihood estimation, and method of moments estimation. And those are the two big ones that a lot of people use, and they're certainly not the only ones. But when you use these APIs in Python for so-called fitting distributions to data, it's really important to understand what's going on underneath the covers. Okay, and that's what our focus will be. But I wouldn't ask you per se to implement these methods, but you could quite easily, knowing after becoming more conversant with these procedures. Excuse me. So let me hide the meeting controls. And again, I have a little bit of a cold. I don't know if it's allergies or cold. I know I'm allergic to Worcester. I found that out last year. Hide floating meeting controls. Okay, so where we last left off, we talked about the relationship between estimators that you calculate these statistics from the data and the ground truth parameters governing the distributions responsible for giving you your data. And we said if they are quote unquote stable, they're reasonable replacements. And we defined what stability is. It's two sort of litmus tests you can think of. One is called the test to see if your estimator or statistic or function of the data is so-called unbiased or and it's consistent. And if it satisfies those two properties, and typically you'd have to prove that regardless of what your statistic is, then you are guaranteed your statistic will be stable enough to be a very good replacement for the unknown population quantity, these population parameters. Okay, any questions about that? To jar your memories. All right. All right. So then we said the two procedures that we're going to talk about in this class are method of moments estimation and max likelihood estimation. And we talked a little bit about what a moment is last time. And we said they use the tools of physics because that was what was available at the time. And they enterprised to reuse what was known rather than completely invent a new method. All right. So when we talked about moments, we used the physics analogy and we talked about torques and forces at distances. And we said with our distribution, if we imagine each mass point as exerting a force, its weight due to gravity, and we have a pivot point balancing a board, and here we have it in blue, each one of these forces at a distance is going to want to make the board tip, exert a torque, rotational force, either clockwise or anti-clockwise. And so we add up all of those moments, and we can do that for the discrete distribution case with a sum, or the continuous distribution with an integral. And we're adding it up, and this gives us, with specificity, a quantity that we can use to calculate all sorts of, or quantify all sorts of aspects of the shape of the distribution. Any questions? No? Jar your memories? All right. And so this idea of moments will tell you things like the central tendency. Where is the center of mass, the balance point, if you will, of your distribution? It'll tell you things such as what is the dispersion of your distribution, or variance, the second central moment. It'll tell you the skew, whether it's so-called left skewed or right skewed, or sometimes when you read it, they'll say negatively skewed or positively skewed. And that corresponds to the physics analog, which way the board will tip. Will it tip to the proverbial left, anti-clockwise, or to the right, clockwise? And then lastly, the fourth moment, we're just mentioning it, kurtosis, which is a measurement of flatness. And as you go to the higher order moments, which correspond to that power of n, you talk about more fine-grained aspects of the shape, and it tends to describe the shape of your distribution as you go further and further and further away in the positive and negative direction, away from the center of the distribution. Okay. Any questions? Does that make sense? Okay. Sometimes when, if you read through some stats books or literature or what have you, they'll talk about the higher order moments. And generally they refer to that as anything over the fourth moment, because typically in most applications, you're only dealing with the first four moments. Okay. Does that make sense? Questions? No questions? All right. And so let's take a look at moments, and we talked about them last time, and we're going to introduce some notation and some terminology. And so here we talked about population distributions, and we also talked about sample quantities. And so when we talk about moments, there are two types of moments to which we refer. We talk about population moments, which are computed using or involved, which are computed using the population distributions or involve the population distribution. Sometimes when I think something, I'll think I said it to you and not realize I didn't say it to you. And then I just kind of catch myself. It's been a long-term thing. But anyways, and so when we note the population moment, we have the kth moment, and we said that k corresponds to an exponent. And we said moments can either be centralized, meaning you shift it, the center, to be about origin, or they can be non-centered. And so notationally, when we refer to a so-called population moment, we use Greek symbol mu, and that subscript k represents the exponent. If we go back 2 slides, or a couple slides, you'll notice here, the nth moment here, we have mu sub k, mu sub n here. I'm just using k instead of n. That corresponds directly to the exponent. And then when it's centered, we said we're subtracting some quantity that's shifting the distribution. And then we're multiplying by the force, which is our probability mass or density. And so going back, when we note the population moment, This is an expectation, or as we've been calling it, a probabilistic average, and it involves the variable of interest, the measurement quantity, exponentiated to some variable k. Okay. Any questions? Any questions? Questions at all? No? All right. And so the term population moment refers to this expectation, but the force involved is the population distribution, whatever kind that might be. And so here we expand that out. We have the non-centered version, or the regular moment. We have our distance from the pivot. In this case, the pivot is considered zero, not the mean, not centered about origin. And then we multiply that by the force, which is our probability mass, and we sum those moments together. That's exactly what our expectation is. It's just your moments, the sum of the moments, or the integral of the moments. And so we also have quantities involving samples. And for these samples, of course, we make the assumption that the force associated with each data point is equiprobable, or is of equal size. And so with that, we have something called the sample moment. And it works kind of just like the population moment, only we're not using the population distribution. And so in that case, you can imagine our force is 1 upon n. So we have the distance from the pivot, that's the quantity, and then we multiply each one by the force, and that's 1 upon n, and we're summing all of those moments together. Does that make sense? Any questions? And so notationally, the convention I'll adopt here, and it could be a little bit different for notation depending on what you're reading, is that the population moment will always be mu, where the order of the moment, first moment, second moment, third moment, fourth moment, is that subscript k. And for the population moment, we adopt little m, where m means the population moment, where population moment is noted as n. And k, that subscript for that little m, is the order of the moment, the exponent that we use. And that could be the first population moment, the first sample moment, the second sample moment, the third sample moment, the fourth sample moment. And what makes it the sample moment is this probability, that force, 1 upon n. Because if you're dealing with samples, you don't really know what the population distribution is. So that's often the assumption that each one of those forces involved in those moments for each one of those samples is the same size. Any questions? No questions? Make sense? All right. And so the idea then is that the sample moment is a very good estimate or replacement that you can compute from the sample data, these measurements quantities that you take. And so the first sample moment, if we take our m sub k and we substitute k to be 1, that's nothing more than the sample mean. You sum together all of the measurements and then you divide by n. But we're not going to really say divide by n here. What we're going to say is we're multiplying each measurement by that force to compute the moment. And we want to know what the collective contribution is when we sum together all of these moments. And that will tell you something about the shape of the distribution. Okay. Does that make sense? No? All right. And so here's another moment. We said we can centralize our moment. And when we centralize the moment, we're taking the center of these points and we're shifting it, that center of mass, so that it's about origin, it's about 0. And we said the reason for that is that when the distribution moves its location, shifts to the left or shifts to the right, nothing has changed about its shape. So this statistic that we compute when we talk about the sample moment, it should not be brittle or change when you change the location. And so that's the whole point of the centralized version. And so in this case, we're going to look at the centralized population moment. And again, we say mu sub k, and I forgot the little apostrophe. That's a notation error on my behalf. We say the expectation of that measurement minus the first population moment. The first population moment is the mean. And so what you're doing there is you're taking each measurement and you're shifting it so that the center of mass of the entire distribution is now over 0. And that's how you make it less brittle or non-brittle two location changes for your distribution. And so here we have the central population moment. We subtracted off mu sub 1, our first population moment, from each measurement, and we preserve that aspect of the notation where we have k being the exponent. And so here, mu sub k for the centralized population moment is the expectation, or probabilistic average, the force or probability times the distance from the pivot. The pivot is now the mean, mu sub 1, and so we're still measuring the distance times the force, and we're exponentiating that distance to some power k. Does that make sense? All right. And so here, if we expand it, we have each measurement, and we subtract the population mean, mu sub 1, from each measurement. We exponentiate it to the power k. That's our distance from the pivot, and then we multiply that distance times the force for that particular measurement. Okay. Does that make sense? Okay. And so we also have a sample version of the centralized kth order moment. And here, again, we adopt little m to represent the sample moment. It's the moment computed from the sample, not for the population. And so here we have m sub k because it's the kth order sample moment. And we use this little apostrophe to note that it's centralized. I just didn't do that with the population version. And so our kth order sample central moment, m apostrophe k, is just the force at a distance, and we're summing together those individual moments. We take each measurement, each sample, xi, we subtract from it not mu1, that's a population quantity, we subtract from it x bar, which is the sample mean. The sample mean is that central tendency associated with sample versions of our quantities. Does that make sense? Any questions? No? All right. And so we then, again, this is a recurring theme, we have force at a distance. Our distance is the distance from the pivot. We're centering it, so that distance is relative to the mean. And then we multiply each one by the force, and we're assuming that force is the same for each measurement. That's the 1 upon n. Okay. Questions? No questions? All right. And so we have each one of these sample centralized kth order moments. These are good estimates for the population centralized kth order moments. There's a one-to-one mapping between them. And so the population second central moment, that's our variance, right? And typically in statistics, they talk about them in the framework of moments because what these summaries are really doing is quantifying for you different aspects of the shape of your distribution. And so here's our variance. Again, it's the second centralized population moment, sometimes called sigma squared, or you could equally write it mu sub 2. Does that make sense? Any questions? Okay. And so for the sample version, that's just something called big S squared. And big S squared is m apostrophe. That means it's a centralized sample moment of the second order, okay? And so each measurement, as we said before, minus x bar, sample mean, that's the distance, and the force for each one is 1 upon n, and we're multiplying the distance in each case. We're exponentiating it to the 2 power. Okay. Any questions? No? All right. So one of the observations here with big S squared is you notice this leading coefficient is 1 upon n, right? That's the second central sample moment. But if you were to compute this litmus test over big S squared, it will fail the unbiased test. This is the unbiased, so-called unbiased estimate of the sample variance, of the population variance, or you're calling the sample variance is an estimate for the population variance. And so how this is repaired is the leading coefficient is changed to 1 upon n minus 1. Now, in a typical experimental design, they'll say you subtract 1 for your degrees of freedom. And that comes from this proof for unbiasedness, where it fails for big S squared. They repair it by scaling it by a certain scaling factor, and it results in 1 upon n minus 1. And if you do the proof the test for unbiased for the version of S squared called little s squared that has this leading 1 upon n minus 1 instead of leading 1 upon n, you'll see that it does pass the test for unbiased. And so what that will mean is if you use big S squared with that 1 upon n leading coefficient, if you have outliers or if your distribution is skewed, you're going to get bad results. Okay. Any questions? Does that make sense? All right. And so the big S squared version is biased. It doesn't work if you have extreme outliers or if you have dramatic skews, whether positive skew or negative skew for your underlying distribution. And so one of the things that you typically do in practice is you look at your quartiles and look at how many of your samples fall among the quartiles, and then kind of do a weighted analysis to say how much of my mass is in various parts of the quartiles. And if it's more skewed or collected off in one direction instead of balance in the positive negative direction, that's kind of a hint to say, oh, well, I might be skewed. Okay. Any questions? Does that make sense? And you can always test for outliers as well. All right, so let's take a look at the so-called method of moments procedure. And so all of the work was done for you over about 100 years or so. And if you follow this procedure, it will give you a statistic, a function over data, that is guaranteed to pass these tests of being unbiased and consistent. And so you don't have to do all the work. As long as you follow these procedures, the statistics you get are good replacements for the unknown population quantities. And so there are two that I'm going to talk about, and I'm not sure how far we're going to get to do max likelihood, but certainly we'll get through so-called method of moments procedure. Does that make sense? All right. And so, there's no other way I can think of to make this fun and interesting. I struggled with that, and I'd be happy to hit some feedback ideas about how to make method of moments entertaining as such a thing can happen. All right. And so we talked about many distribution families, and we talked about these closed form functions, and each one of these distribution families are associated with certain patterns of stochastic behavior. And we said when you're trying to mimic or model some system from its data, you study these functions, you study your system, and then you make a good choice to see which of these distributions best matches the behavior, data behavior of the system that you're trying to model. And so the first question you ask is, which one should you use? Okay. And that just requires becoming familiar with the stochastic structure associated with each one of these distribution families. And each one of these distribution families has a parameter associated with it. For example, for the Bernoulli distribution, it had P, the Bernoulli success rate. With a binomial, we had n, the number of trials, and we had p, the success rate. For the gamma, we had two parameters. We had alpha, the number of steps, and we had lambda, the time parameter. Whereas for the exponential, we just had a single parameter, lambda, which was associated with the rate because the exponential is related to the Poisson. It's the time between arrival of events, or sometimes it's called the inter-arrival time. And so every distribution, not just these aren't the only distributions among the distribution families one might classically study. Every distribution has these governing parameters. And the whole reason for inference is that in real situations, you don't know ground truth what those parameters were, but you do know something about the sample size will get your educated guess, your statistic, as it were, measured from the data closer and closer and closer to the unknown. And so every family has a set of parameters associated with it, and you choose the distribution families that most closely match. And that means you have to figure out what your parameters are that you're going to estimate, what estimate you're going to compose. So let's take, for example, you have a system and it's a retail store, and you're observing all of the customers that come through the doors for standard units of time. So a reasonable assumption is that this is well described by a Poisson distribution. And we know the Poisson distribution let me choose a color here. How about dark red this time? We say X is distributed as Poisson, and it is indexed by a ground truth rate parameter, lambda. And so we know that the Poisson only has a single parameter. So what do? You walk through all the different moments, and you're going to equate two things. You're going to equate the population moment with the sample moment. And because the Poisson, if you count the number of parameters, it only has a single parameter, you start with the first moment. So here in this expression, we equate two things. We have the population moment, the first one, and we set that equal to the sample moment, the first one. Now, because our distribution is a Poisson, the population moment we use, i.e. which version of the force, is going to be the population moment, the first one, for the Poisson distribution. So when we sum those moments together, and it's a discrete distribution, so we know it involves a sum, we know that the force we're going to use is the mass function for the Poisson. Okay. Any questions? Does that make sense? Yeah? All right. And so let's do that. Well, we know, okay, an expression for the first moment is E of X, okay? That's the force times the distance from 0. And we know the first sample moment is just X bar, okay? So you equate them together, and we know the expectation for the Poisson is lambda. We get lambda equals X bar. Okay, well, that was easy. Some of them are more straightforward. Some of them involve a few more moving parts. But what we've done here, we've made a modeling choice. We count the number of parameters it has. And then for each parameter, the first parameter, the second parameter, the third parameter, we set two things equal to one another. That order moment for the population equal to that order moment for the sample version. We equate them, and then we solve for the parameter value. Does that make sense? Any questions? Okay. Now that's the simple case. We'll have a case that's a little bit more complex, but I wanted to show you what the procedure was before proceeding to the more complex case. Now, of course, this lambda, you'll notice here, and that was not a typo, we have hat. Anytime in the notation that you have hat, you pronounce that an estimator, right? An estimator for. So lambda hat is the estimator for lambda, where lambda is that parameter for the Poisson. And so you'll notice here, we have lambda hat is equal to X bar. This X bar, that's a statistic. If we expand out what that is, it's the ith measurement times the probability of that ith measurement. That's a function over, probability. It's the ith measurement times 1 upon n, which is X bar, right? That's a function over the data. I'll just scratch that out. Does that make sense? Now you could just code this up in Python. You slice out a column, and then you just call the sum method attached to the series that you get back. Okay. And so now sometimes in the literature, you will see this written as lambda hat MOM. And what that subscript or that index or that word MOM in the subscript, it's a nod to tell you this is how I arrived upon calculating this particular statistic. And typically in the literature, when you talk about it mathematically, you need to tell the audience what procedure you use to get this particular statistic that you're using as a replacement for the unknown population quantity. Does that make sense? So that's just sort of a terminology practice. Because if you said, oh, I have this data, I computed my statistic, everyone reading it is going to say, oh, well, how did you compute this? But once you say lambda hat MOM, everyone knows what you did in order to calculate that. Does that make sense? Okay. And so for the method of moments, first, like any modeling problem, you think long and hard about the system that you're trying to analyze or you're trying to mimic. And then you select a distribution whose structure and the stochasticity fits with the behavior, the data behavior of the system under study. Okay. And then some of that could be, gosh, well, does the shape of the distribution the pathological shape of the distribution family you enterprise to use doesn't match the shape of the data that you have. That's why you do your initial visualizations of the data through a histogram to try to convince yourself that you've, in fact, made a good choice for your modeling distribution. So then you take your model that you're proposing and you count the number of parameters. Now, some models have a lot more than 2 parameters, but in this class, that's the largest number of parameters that you're going to have for the distributions we're considering. So once you have your modeling distribution, you count the number of parameters, and this number K we're calling, for the number of parameters for your distribution. So now you calculate your first K population moments, the first one, the second one, the third one, through the Kth population moment. Then you compute your first K sample moments. Sometimes it's called the empirical moments because it's from data. So that would be the first sample moment, the second sample moment, up to and including the Kth sample moment. And then you just equate them with one another. So you equate the first population moment to the first sample moment. The second population moment, you equate that with the second sample moment, and so forth up to that Kth order. Okay. Does that make sense? Any questions? No? All right. So then you solve. You solve for the parameters because the sample moment, it's from the samples and it's going to give you a value. The population moment is from the population distribution, and the free variable there is going to be the parameters. Right? So you're going to solve for that parameter, and it'll give you a definition for it as a function over data, as a statistic. Okay. So yes, you effectively match moments. The first population one with the first sample one, the second population one with the second sample one. And then you solve for the unknown, and that's guaranteed, not always, in some pathological cases it's not, but for the most part, this will give you an estimator, a statistic, that is a good replacement for the unknown population quantity. Does that make sense? Any questions? And if you're interested in how they get to this, I would recommend you take a graduate level statistics course, and they'll talk about something called the moment generating function, which gives you all of these moments that you can use. Well, not the sample one, but the population ones. Okay. All right. So let's have a more complex example. And this is involving the gamma distribution. And let's say you want to know the effectiveness of your processor. If you go into any Unix command line and you issue the command top, T-O-P, hit enter, it'll show you something that looks like this green box. You can get the same information from the Windows Task Manager, but what it shows you, among other things, is how much processor time each one of the programs in execution, the processes on your system are taking. And it'll also, in some variations, show you the wall clock time from the time you started it to now, how long it is running. And so let's imagine then we wanted to model by the performance of your processor, and we sampled 30 processes that are running on your system. So you ran top, you looked at the CPU time, how much time each of these 30 processes spent on your processor. And so here, these would be in milliseconds typically. And here are some measurements, 3 rows of 10, so we have 30. And so what if we wanted to model the total amount of time on the processor taken by these 30 processes? Okay, well, we could absolutely model this as a distribution, but let's imagine now we don't know at this juncture what that distribution might be. Does that problem make sense? Any questions? No? All right. And why would you want to do this? Suppose you have a server environment, you have 1,000 processors, you want to know how much utilization is being done. You would take the total CPU time, and then you would look at the total time running, and then you could compute what percentage of the wall clock time is actually being spent for processes running on the processor. Now, you might be wondering, okay, Holness, well, wouldn't it be taking all the time? Why would it be less? Well, some of the time is spent loading your processor from disk to memory and loading parts of your process from a special part of disk called the backing store onto and off of the processor. And so if your system is more efficient, it'll spend more time actually executing your processes on the processor and less time shuttling things on and off the processor. If your system is less efficient, it'll spend more of the time shuttling things on and off and less of the time actually executing on the processor. And so if you have a data center, you have a lot of these racks and they're populated with these pizza box form factor server instances. You could easily have thousands of processors running on your system, and you might enterprise to model how efficient your whole data center is. Because if something's not working, that efficiency is about money. You're spending time keeping these things running, but you're not spending as much of that money on actually running things versus shuttling them onto and off of the processor. Does that make sense? Any questions? And so this type of modeling is really, really important when you're trying to assess efficiency for certain types of applications. So we have 30 of these time measurements, and we can model this in some fashion. So we compute a histogram, and we have a distribution here. If you kind of imagine the envelope, it's right tail, kind of tails off to the right. If you were to imagine this as a set of forces on a board, it's going to tip to the right. So it's positively skewed or right skewed. And so when we look at this, we think about the form of this stochasticity. Well, it traffics in time, okay. The two ones that we talked about that traffic in time is the exponential and the gamma distribution. And here we have a bunch of parts. We have 30 parts, and each of them takes some time. Well, that more fits the gamma distribution. And if you were to sample from a gamma distribution and tinker with the alpha value and the lambda value, you would get something that looks like this. So let's think about, all right, this looks like a gamma. It's real valued, it's time. We know gamma and exponential, but the distinguishing thing is that here we have these parts. We have 30 parts. Now, when we talked about this idea of algorithmic execution, it can be steps in the same process, but it can be a bunch of different parts, each of which takes some amount of time. Does that make sense? Any questions? All right. So we have our gamma distribution, and that's what we're going to enterprise as a result of understanding the system structure, as well as looking at a visualization of the distribution. Okay, so it's very gamma-like. So let's assume that this collection of 30 CP process times are gamma distributed, okay? So we remind ourselves what the mean and variance, or now we're going to say the first moment and the second central population moment. Now here, of course, I got the notation right. I have that little apostrophe to note that it's a central version. So we have two parameters for the gamma. We have alpha, the number of steps, and we have lambda, the time parameter. So k is equal to 2. So we need the first two population moments, and we need the first two sample moments. And we're just going to use, for the second moment, second order, we're going to use the central version, which is the variance. Now, you might ask, well, how did you know to use the central version? You could try using the non-central version, and you'd find that when you did the calculation, it doesn't work very well, okay? Does that make sense? Any questions? No? All right. So now, okay, we know what the first population moment is, and what the second central moment is. That's just the mean and the variance. And we know what that is from the gamma distribution from our treatment before. Now, if you didn't know, you'd actually solve for these yourself, but that's not part of this class. Okay, any questions? No? So we have a so-called two-parameter model. And if you look in the literature, it'll call it the shape and the scale parameter, but we're not going to talk about that treatment of our distribution families. So that means we also need the first and the second sample moment. We just calculated the first and second population moment. So now we're going to do the same thing for the sample moments, which was that next step in the method of moments estimation. Okay, so the kth sample moment for k equals 1, well, that's just the sample mean. And we'll call that little m sub 1. And the second central sample moment, well, we write that out. We have 1 upon n times the sum of each measurement minus x bar raised to the k power. Here, k is going to be equal to 2. Does that make sense? All right. So let's go ahead and using these numbers, because they're sample moments, you can actually compute these values. And so our sample mean, our M1, is going to be just over 48, and our M2 prime is going to be about 679 and change. Okay. All right. So now that we have them, let's go ahead and let's equate them. We're going to equate the first population moment to the first sample moment, and then we're going to equate the second central population moment to the second central sample moment. Okay. So if we go ahead and we do that, well, I'm going to do that. And here we, excuse me. So we have here alpha upon lambda. That is our first population moment. That's just the expectation of a gamma is equal to M1. And then we have mu prime 2 is alpha upon lambda squared. That's the variance of the gamma distribution, okay? And we're going to set that equal to M2 prime. So literally, you just match moments. The population moment matched with the sample moment of the same order, which is very, very important, that of the same order part. Any questions? No? All right. Now, of course, all you do is just call a function in Python, right? So why are we doing this? It's really important to understand what's happening underneath the covers, especially if a procedure you do doesn't work or it's biased. You need to really understand what's going on underneath. Okay. So we go ahead and we say, okay, let's do a little bit of algebra for the first equation here, and we have the second equation down below. And so we have alpha upon M1 is equal to lambda. And this gives us an expression for lambda, okay? And we're going to then substitute this definition for lambda everywhere here. We see here there's a lambda squared. We're going to substitute the result for that first equation into the second equation. Does that make sense? Any questions? No? All right. So now we do some calculation. Let me just get to the punchline. We have alpha is equal to M1 squared over M2 prime. And then we have lambda is equal to alpha upon M1, where the M1 and the M2 prime are 48 and change and 679 and change respectively. Okay. Any questions? Does that make sense? So it's just a little bit of algebra. And so this gives us two expressions. We have now an expression from the data for lambda, and we have an expression from the data down below. That's our lambda for alpha. And so you can now calculate these as things that you can define over data. And these are going to be our method of moments estimators that we're going to use as substitutes for the ground truth population parameters, because nobody knows ground truth what alpha and lambda are for the true population distribution governing your processes running on your processor. And so notationally, we call our lambda hat, and we call our alpha hat to note that they are estimators, they are statistics, functions over the data that we're going to use for replacements for lambda and alpha respectively. And given our values for M1 and M2 prime, we can actually compute them from the data, right? And I've done so. So in this case, you'd have lambda hat is equal to 3.4 and our alpha hat 0.07, and you just have to normalize that and call it 1, and or you can't really call it 0. Okay. Any questions? Does that make sense? All right. And so you would note it as lambda method of moments, lambda hat MOM and alpha hat MOM respectively, so that when you write about it, people will know, your audience will know that you use method of moments estimation. Okay, any questions? So a long approach to say, follow this procedure of matching moments and solving for the unknown for each parameter will give you a statistic that is a good replacement for this unknown population parameter. Does that make sense? Okay. And so if you're trafficking in some Python API, the SciPy APIs will do this for you, right? And one of the choices you can give it is the way it's going to calculate the estimator, right? Method of moments or max likelihood. Okay. All right. Any questions? No? All right. So for this next one, we have half an hour. We're going to motivate this, and I try really hard to make this material as fun as you can make this material. Um, we're going to have a motivating example. So let's imagine James Bond, who is a spy, oops, uh, who works for the British clandestine service, has retired, and oh, I can't do it. I was going to play a song, but no, I don't want to do that. Hit the wrong button. Let's do that again. Let me see. There we go. Nope. There we go. All right. I just killed that intro. All right. So let's imagine Agent 007, James Bond, has retired from the British clandestine service. Now, Mr. Bond, Agent Bond, is a little bit kind of dissatisfied with retirement. And this international man of mystery has decided to open a coffee shop. And he needs help. He needs help from you to build a mathematical model that he can use to do forecasting for his shop, his coffee shop. All right. Anyways, so we have Agent Bond, and Agent Bond, being a spy, working for or a retired spy for the clandestine service, observes everything. Spies are really, really good observers of things. And so, in some 15-minute window of time, he observes there's a person who comes in and standing at the front desk. Now, of course, like any entrepreneur in the beginning, you kind of wear multiple hats. You do a little bit of everything. If you talk to someone who's ever opened a coffee shop, you're going to be doing everything. You're going to be staffing the bar, bussing the tables, everything, ringing people in. And so he notices his spy skills of observation are really good at noticing what's going on. So he sees one person come in a certain period of time. At the next instant, he sees that there are three people who've now come to the coffee bar, waiting to get their order, waiting to place their order. And he does this again and again and again. And maybe in this next period of time, he sees four people come in to his coffee shop. And so he asks you for help and to choose a model because the enterprises to do some forecasting while his powers of observation are quite well tuned, his modeling is not so quite well tuned. Okay, and so let's look at the max likelihood procedure, and it has a bunch of moving parts. It involves optimization as well as selecting your model. Okay, and so first, just like the method of moments example, you are going to think long and hard about the problem at hand. Now, of course, this particular problem traffics in time, okay? Once you thought long and hard, that might involve some visualization. You're going to select a distribution or distribution family whose behavior, structure of stochasticity, makes sense and matches the system under study. So we have events, the appearance of customers arriving in time, and in this particular case, for this example, it's every 15 minutes. Okay, so now for the max likelihood procedure, you evaluate the mass function or the density function on each one of your data points. That's going to give you a huge function. And in that huge function, what we'll find, there's our free parameters, and those free variables, I should say variables, not parameters. All the parameters in your distribution are going to be free variables in that huge function, resulting from the evaluation of your mass function or your density function on each measurement, actual measurement. And so now you take each one of these evaluations and you put them together by taking the product of these so-called likelihoods, these evaluations of your mass or density function on each data point. And your parameters are free variables, and you solve for them. and you solve for them by solving the optimization problem. And we'll give a kind of high level, little bit of a background in stochastic optimization. You could actually get a PhD just in optimization, so we can't give it too much treatment in this class. Okay. Any questions? Does that make sense? All right. And so let's take our modeling example. And for this, Bond's Coffee Shop, we have windows of observation. And for each window, we're going to say the occurrence of a customer is an event. And we know at this juncture, it's well modeled by a Poisson distribution. So one of the things you could do is visualize your data and convince yourself that that's Poisson-like in its shape. You could also, now that we've had these sampling routines, you could sample from a Poisson for different values of lambda, and it'll show you different pathological shapes that the Poisson distribution can take on. Now you notice here, as lambda increases, here we have lambda as 1 in the black through lambda is 9 in the purple, and we call that our rate parameter. Now, one of the things you'll notice for this sampled version, as we increase lambda, the mode, it starts out as right-tailed, but the mode starts to shift more and more to the right until it's almost completely symmetric. And so what this sampling from a distribution for fixed values of lambda does, it tells you what does a Poisson distribution look like for various instantiations of our rate parameter lambda. You can do that and visualize it alongside visualizing the actual data that you have through a histogram. Not only does the behavior match events in time, where it's a constant delta t throughout the course of time, but the shape of the distribution, it makes sense. It looks like a Poisson. You know, if you visualize your distribution, and let's imagine when you did the visualization of your actual data, if it looked uniform or close to uniform, kind of straight across, you'd say, oh, that's weird. It doesn't look like a Poisson. But if it is Poisson data, it's going to look like a Poisson, this kind of skewed version of the graph. Does that make sense? And so one tool that you have, not just your visualization, not just your matching the functional behavior to the behavior of your system, you can also sample from various distributions to see, does it kind of look like one of these for various versions, in this case of the Poisson or the gamma or what have you. Any questions? No? Does that make sense? Right. So you have a lot of tools to help you in your decision, along with just looking at the properties. The properties are important, but it's not the only thing that you can do. All right. So, but you know it's Poisson, but you don't know which particular lambda to choose. Yeah, you could visualize your data and eyeball it, but that's not a very good choice. You want to calculate things from the data. Let the data tell you what it should be. So you don't know what lambda to choose. So how are you going to find the lambda, knowing that it's Poisson, that most closely coincides with the data that you have? Okay, well, why not choose the lambda for your Poisson assumption that best describes the data that you have? Well, that kind of seems to make sense. But how do we say best describes? How does that work? What do you mean best describes? Okay. I've been trying to release this pen. It's not letting me. Usually escape releases the pen, but escape is hooked to the floating meaning controls. Okay. So let's look at what best describes the data means. We know that our measurement quantity, the customers that arrive in time, we know or have a good sneaking suspicion. We decided upon the Poisson, and we know the Poisson has a single parameter, lambda. So we have the mass function as follows: lambda to the x, e to the minus lambda upon x factorial. That's the mass function of the Poisson distribution. That's our force, okay? Now we know that in the first instant, we had one person, the next instant, 3 people, and in another instant, we had 4 people, where each delta t is consistent, our 15 minutes. And so let's evaluate our mass function using that x equals 1 that we observed in the first 15-minute delta t. Okay, if we can do that, that's the probability of observing one person come in given some lambda. Now you notice here that we have lambda in the mass function. We haven't filled that in because we don't really know what it should be. Okay, well, we can still express that function. And the only thing in this expression, this evaluation, that is a variable and not a value, so-called free variable, not defined, is this lambda. All right. So let's evaluate it for that occurrence of 3 people in that next instant. Okay. Here, everywhere we had x, we substitute a 3. Okay. Again, the free variable in this expression is our lambda. So for each evaluation, up to including the last data that we have, we evaluate it. And for each of these expressions, the free variable is this lambda. It's the same lambda. And why is it the same lambda? Because it's a so-called IID, independent and identically distributed sample. Because it's identically distributed, it's the same Poisson. So we can assume this value of lambda, whatever it is the same as this value of lambda, whatever it is the same as all of these evaluations. Does that make sense? Any questions about this? No questions? No? A little too much for 9 in the morning? Yeah. Okay. All right. So now we've observed some number of measurements, n many, and for each of these observations, we evaluate the mass function on them. And for each one of these evaluations, that lambda is a free variable. It's undefined. We have lambda here, and that's the only thing that's not defined. Okay. So this idea of best defines the data. How are we going to do that? Well, in max likelihood, this idea of best description is that particular lambda such that, or that parameter, such that when you evaluate this mass function on each data point, those probabilities are the biggest probabilities that you can have. Does that make sense? And so then this idea of best describes is for each one of these evaluations, choose a lambda that these evaluations are the biggest probabilities. That's the maximum likelihood, right? And so MLE, the max part, talks about maximizing the likelihood function or the evaluation of the mass function or density on each one of the data points that you have, okay? But there's a little bit of a problem here. And the problem is that we have n many evaluations of the mass function on each of these n many samples. We need somehow to put them together because right now they're individual. That's a hint for the solution is this independent part of the IID assumption. Because they're independent, for an independent distribution, for independent probabilities, the occurrence of those measurements together is the same as the product of the individual occurrences, okay? So here, we want the parameter or that version of lambda that leads to the highest joint probability. And we know we have independent and identically distributed samples or measurements. So we're just going to multiply together, that's this super product here, each one of the individual probabilities. And so we're going to say the first evaluation times the second evaluation times the third evaluation and so forth. Okay. Now, this is particularly messy. You have the product of a large number of things. Okay. Well, effectively, what's that's doing, if we go back to Bond's coffee shop, we have the first evaluation for one occurrence of an event, the next evaluation for 3 occurrences of the event. We're going to multiply all these together, which is exactly what this super product is expressing. That is a function. It's a function that is the product of n many things, where each of those things is an evaluation of the mass function on that observation, a likelihood. So we have the product of n many likelihoods. Okay. Well, what are we going to do with this? And we'll probably end with this part of the module. With this max likelihood estimation approach, now we have a way of expressing this function that talks about putting together all of these likelihood observations. So we want to find the value of lambda where this reaches a maximum value. Okay. Well, that's the domain of optimization. But this is a little bit messy. We don't like this function. We want to make this a little bit simpler. And the reason is because of this multiplication. So we're going to make a transformation on this expression. And this transformation is some function that we compute on it, and it's going to change its form. But this particular transformation is a so-called monotonic transformation, and that's particularly important. So let's take, for example, if we had a sequence of numbers like 1, 3, 7, and 12. Okay. Well, if we were to order these numbers in non-decreasing order, and I say non-decreasing instead of increasing because it means from one number in the sequence to the next, it can either get bigger or it can stay the same. That's different from get bigger each time. So we sort these numbers in non-decreasing order, and we know that 1 is less than 3, 3 is always less than 7, 7 is always less than 12. There's a particular ordering associated with them, okay? Now, what a monotonic transformation is, it changes the shape, it changes the value, but it preserves the ordering. And the reason why that's important when you transform something, when you're trying to find the minimum or the maximum of a function, is because there's going to be a value, and associated with that value of lambda is going to be an expression for this product of terms that is going to be the biggest one, right? So we don't want to damage the ordering of these values. If we were to take the natural log of each of these numbers, ln1, ln3, ln of 7, and the natural log ln of 12, well, that transformation of taking the natural log, it does not change the ordering because the ln of the first term is less than the ln of the second term, less than the ln of the third term, is less than the ln of the fourth term. And so we're going to change this expression, this superproduct, but we don't want to damage the ordering of the values it would take before we made that change. Does that make sense? And that's a so-called monotonic transformation. Because if we want to find the value of lambda for this expression that involves products where it reaches its maximum, we don't want to change the ordering of those original values of lambda. And that monotonicity in the transformation preserves that. Okay. Any questions? Oh, all right. And so logarithm is a monotonic transformation. So is multiplication by a scalar. If I were to take my numbers here, and let's say I said multiply by 2, wrong? Well, times 2 for the first one is 2, times 2 for this one is 6, times 2, 14, times 2 is 24. So the times 2 transformation, it preserves the relative ordering of that particular term. The first term times 2 is still less than the second term, less than the third term, less than the fourth term. So we have some tools here where we can change the form of this problem and still solve for when it reaches its maximum. And as long as we transform it or change the superproduct with a monotonic transformation, we can still find the maximum. Does that make sense? All right. And so natural log is a monotonic transformation. And if we take the log of the superproduct, well, the log of terms multiplied with one another turns product into a sum. Well, that's kind of convenient, okay? So we have the log of the product is the sum of the log of that term that's being multiplied with itself. Okay, does that make sense? Any questions? All right. So now we change it to a sum, and a sum is a lot easier to work with when you're trying to find the maximum of something. Okay, so now, and we'll probably end with this, we have the probability mass function for the Poisson distribution. Recall that it's an evaluation of this mass function for x equals each one of those observations. So now we need the log of this mass function. Well, log says that if I have the log or natural log of x over y, that's the natural log of x minus the natural log of y, okay? So we have the numerator here, log of that, minus the denominator, the log of that. In the numerator here, we have a product of terms. The log of a product is the sum of the log of the individual terms, okay? One of the terms is an exponent. The log of a to the x is x ln of a, okay? And then the log of e, natural log of e is the inverse function. That's just whatever that exponent is, okay? Any questions? Jar your memories? Some algebra stuff? Or maybe it's trig, I don't remember when they teach that. But anyways, so if we do the log of the mass function, we get minus lambda, that's due to this term. We get plus x ln lambda, that's due to this term, and it's plus because they're multiplied together. And then we have minus ln of x factorial. Well, it's minus because this is in the denominator, and it's the ln of the x factorial. Does that make sense? Any questions? All right. And so now we have a sum due to this monotonic transformation for log, and that log also transforms the mass function for the Poisson. And so substituting, we have now this new expression, which is just the sum of minus lambda plus xi ln lambda minus the natural log of xi factorial. Okay. Does that make sense? So this is just a substitution, knowing what the natural log is of the Poisson mass function, and that product turned to sum because of that log. And so it's a monotonic transformation, and we know it's not going to damage the ordering. So if we do the optimization that solves for the maximum of this expression, that result, that value of lambda, is also going to solve for the maximum for the original expression that involved our product. Okay. Any questions? All right. So I think this is a good stopping point. We want to find the value of lambda that maximizes this particular expression. And it's a lot easier to do that when you have a sum than it is when you have a product. And the monotonic transformation affords us the ability to do that. Okay. Any last questions? No? All right. So I will certainly post some stuff about max likelihood and method of moments. I wasn't going to post it today because obviously there's an exam on Wednesday, but we'll continue on with the balance of this material on Friday. Okay? All right. Any last questions? So we'll end here. I don't want to break the next part. All right. So with that, we'll end there. I'll see you all on Wednesday, and look forward to seeing your exam solutions in the future.